Scientific notation. Scientific notation is really just a shorthand for extremely large or extremely small numbers. You take a number that is extremely large or extremely small. Generally speaking, it has a string of zeros either at the beginning or the end. And you're going to express that number as a number between 1 and 10 that's multiplied by a power of 10 a certain number of times. Now, the part of the number that's made up of the significant digits, or the numbers that aren't zero, is called the mantissa sometimes. And the part that tells you how big or how small the number is, that's the exponent that goes on the 10 in scientific notation form, and that's known as the order of magnitude. Magnitude tells you how big it is. So, we want to take a number and we want to convert it to scientific notation. To do that, what we want to do is we want to eliminate non-significant zeros. That means the zeros that are just a string at the beginning or a string at the end. They really don't represent measurements or counts. They're mostly just to keep the significant digits in the correct place value. So we eliminate the string of zeros. We find the mantissa by putting a decimal point right after the first digit, whatever it is. And that will automatically be a number between 1 and 10. To find the order of magnitude, then you count how many places you would have to move the decimal point from where you just put it to get it back where it actually belonged in the original number. If you move the decimal point to the right, then your order of magnitude is positive. If you have to move the decimal point to the left, oops, there's a typo on my PowerPoint. If you must move the decimal point to the left, the order of magnitude is negative. So, what do? We have this big long number, and it's a large number. First, we have to decide our significant digits. The string of zeros we want to eliminate are the ones that are out there by themselves. We can't eliminate a zero that's between two other numbers because then it is an actual measurement, not just a placeholder. So my mantissa, it starts out as 309, but unless I put a decimal point somewhere, that's not going to be a number between 1 and 10. If I put my decimal point after the first digit, 3.09 is a number between 1 and 10. Scientific notation always has a times 10 component, and then the exponent tells me how many times I would have to move the decimal point from where I just placed it to put it back where it belongs. I placed the decimal point here between the 3 and the 0. I need to move it to the end of the original number. So this is just counting. If I multiply by 10 one time, that'll move the decimal point one place. 2 times we get it after the 9. 3, 4, 5, 6, 7, 8, 9, 10. I have to multiply by 10 times to put the decimal point back where it belongs. And it is a positive 10 because I'm moving the decimal point to the right to put it back. In the second example, I've still got this string of zeros I'd like to eliminate, but that means my number is way small because my number is after the decimal point. It doesn't matter. When I form my mantissa, I take my significant digits, that's the digits that aren't zero unless they come between other numbers. 285 is not between 1 and 10. I have to put the decimal point here to make it between 1 and 10. Scientific notation always has a times 10 component. And now I have to count. If I put the decimal point here, how many times do I have to move it to put it back where it originally came from? I'm moving it to the left So that's going to be a negative exponent, and then I just count spots again. Once would move it here, 2, 3, 4, 5, 6, 7, 8 times puts it back where it was. So my scientific notation is 2.85 times 10 to the negative 8. If I want to go the other way, if I'm given scientific notation and I have to write a number in standard form, then I start with the mantissa. Now, write your mantissa without the decimal point. What happens is if people copy down the mantissa with the decimal point and then they do their little loop-de-loops trying to figure out where to move the decimal point to, they forget to erase the original decimal point. So you end up with a nonsense number that has 2 decimal points in it. So write the mantissa without the decimal point. Then count from where the decimal point was, however many times the order of magnitude tells you. Now, if your order of magnitude was positive, you're going to move the decimal point to the right. If the order of magnitude was negative, you're going to move it to the left. If you move the decimal in either direction and you have holes, you fill in those holes with zeros. 6.12 times 10 to the 7th. I write down 612 without a decimal point. Now I have to figure out, what do I do to get this decimal point moved 7 times? It was here between the 6 and the 1. Move it 2 times gets me to the end of the numbers that I have, and I still have to move this decimal point 5 more times to make it a total of 7. So between the 2 and that decimal point, I need to fill in 5 zeros. And it helps if you put in the commas. Just helps you keep track of where you were and counting. It's a luxury you have when your number gets big, not the same luxury when it's small. Now my mantissa here is 2.16. I'm going to be moving my decimal point to the left. So I don't want to write 216 right here because I need to move my decimal point this way. That's going to be tragedies. So what I want to do is, I know the 216 is going to be at the end of the number if I have a negative exponent. Now when I look where the decimal point used to be, I need to move it 5 times that way. Once it gets in front of the 2, then I need to go 2, 3, 4, 5. That's where my decimal point should be, which means I need to fill in 4 zeros. And that would be my scientific notation. That would be my standard notation. Calculator notation, you need to know that because really that's the only reason we're talking about this. If your calculator gives you an answer, the calculator notation is not an acceptable way to answer a question. So what the calculator does, it doesn't generally give you that times 10. Instead, it'll give you the mantissa, and instead of times 10, you'll see a capital E, and then you'll see the exponent, the order of magnitude. It won't be written as an exponent, it'll just be written as a number. If your order of magnitude is negative, it'll just look like that. So you want to be able to look at calculator notation and understand that you never want to write that down. If you see this for an answer, you need to either write it as scientific notation or go ahead and change it all the way to standard notation. One of the things that we have to do is also to compare numbers that are in scientific notation. If all the numbers are in scientific notation correctly, then the only thing we have to compare is the orders of magnitude. The larger the order of magnitude, the larger the number. So if we're looking for a large number, then obviously we're not going to look at the negatives. Large numbers are going to have positive orders of magnitude, and we're going to look for the one that has the largest. Now, had I been looking for the smallest of the numbers, I would have been looking opposite. Instead of looking for positive orders of magnitude, if I had the option, I would be looking at the negative ones. Those are the small numbers, and the one with the most negative number would be the smallest.